Hey guys, welcome back. So we are at episode number 3, and in this episode I'm gonna explain 3 very important questions which might arrive in your next VLSI interview. So please be attentive. Before I start, please like this video. And the first thing is that, and it's actually very basic thing, but which we might miss, because anytime we draw the schematic of our inverter, that time one thing we do specially, and that is we just forget about our body terminal. So if I ask you, a MOSFET, how many terminal does a MOSFET have? You have the right answer, right? 4 terminal. If you don't know and you are thinking it is 3 terminal, then it's okay, we will explain this thing here. But yeah, if you are saying it is 4 terminal, then it's perfect. We have 4 terminal MOSFET. So see, anytime we draw our schematic, what we show one terminal here, second terminal here, and third terminal here, and we tend to forget the 4th terminal. And it's all okay, because 4th terminal probably is redundant here. Why? Because your 4th terminal is connected with source only. If I change the color, your source terminal only, this is your source and this is your source terminal only. Because for a PMOS, if we have a PMOS, then your source and your body terminal are connected to VDD. So here we have our first question for the day, and that is why our body terminal of a PMOS should be connected to VDD. Continuing with that thing, if we go for NMOS, then this terminal here have your source and the body terminal, and our body terminal always connected to ground. So this could be a very basic, very fundamental but very important question whenever you go for your interview. Probably in your CV you have written that you have done many projects which utilize the schematic capture EDA tool, but if you haven't done that thing with 100% of your attention, then you probably miss out onto this answering this question, and their interviewer will catch hold upon you that you haven't done that project on your own. And that thing happened with me. Like first time I went to lab to draw or to capture the schematic of an inverter, I asked my lab attendant, because whenever I went there, I have 4 terminal of my MOSFET, and I know how to connect my 3 terminal because it is in the book. But I don't know how to connect the 4th terminal, because in book or anytime we write in exam, like here I am writing it, we just ignored the 4 terminals. And probably this could be the case of you, and it's all normal. And this is the first question of today. So why it's connected to VDD? So if I want to draw this thing with mentioning every detail, then it should be drawn like this. This is your PMOS and this is your NMOS. These are connected, and then here actually we have the body terminal, and your body terminal and your source will be connected to VDD, and your source terminal here and your body terminal of NMOS and the source terminal will be connected to your ground. And if we see some other example, for example a NAND gate, CMOS NAND gate, you can see from here that your body terminal of PMOS are connected to VDD and the body terminal of NMOS are connected to ground. This is the exact way whenever you go to any EDA tool to capture your circuits. To give this answer, we need to see the cross section of the exact device, because these are schematics, these are just symbols. This doesn't show us the exact practically MOSFET structure. So to see the practical MOSFET structure which is actually coming in your physical world, and that is something like this from the cross section view and something like this from the top view. Now you will be very much confused if you haven't never seen this thing, that what is this. So let me explain you. See, in book you generally saw your NMOS, so it would be N plus. So this could be your gate, this could be your drain, and this could be your source. So this is our NMOS, and anytime we have our substrate, then we assume that it would be of P type. So that means this is my substrate here, and I am seeing just the cross section view. If this is your substrate, and it will have some width here, right? So we are cutting it here directly, and we are seeing the cross section view here. So this is your cross section view, and this is your P substrate. But now, to manufacture a inverter, we also need a PMOS, and PMOS could be manufactured in a N type substrate only, but this is our P type substrate because we need to make the NMOS. So for PMOS, what we do, and that is we do implants of N plus doping, and which is called N well. So after doing that, we do our P plus here and P plus here, and we build our gate and oxide layer, and we called one of them as drain and another as source and another as gate. So this is the structure, but this is still not similar to this one, this structure, right? Because here we have something extra, and that is this part and this part, and that's are actually your tap cells. What does tap cell means? Because see, we have said that our MOSFET have the 4 terminal, but again here and again here we can see only the 3 terminal. So where is our 4th terminal? And our 4th terminal is actually this one. This is our body for NMOS, and this is our body for PMOS. And that's why in this picture you can see our N-well is extended little more here, and we are again doing N plus here because this is my body terminal. So I need to have a conductive terminal of a body, and conductive means the more the doping. So that's why N plus here we do N plus implant, and we call this is as our body. And here also we do, because this is NMOS have the body of P type, so we do P plus doping here, and we call it is the body for our NMOS. Now if you see it more correctly or more closely, then you can see here one thing, and that is we have here some BJT like structures, because your BJT are nothing but are your P type substrate, then we have N, and then we have P. So we call it as PNP, and if I do reverse it could be NPN. But for the current interview, VLSI interview, we won't go very deep to BJT, because BJT are not very much used in current CMOS technology or the current chips which we are dealing with, right? So I'm also not familiar with BJT too much, so we won't go there deeply, but we want to answer our question, and that is why the body of NMOS is stepped to ground, and why body of PMOS is stepped to VDD always. And that is to solve this issue, because if you don't tap this to ground, see, it is a P type substrate, right? So if your P type get some more potential than your N type, then what will happen? Just recall, and that is called your forward bias. If your P side have the more potential than the N side, it might get forward biased, and if anything get forward biased, then that would give a path for current, right? So for example, here if we haven't tapped this body to the ground, and why ground? Because ground is probably the lowest possible potential available in our circuit. There could be minus negative also, but that have some other case, but in general 0 potential or the ground could be the lowest possible potential we have, and we want that our MOSFET should never get forward biased in this junction. For example, here we have one junction, we have a junction here, right, N and in between P, because source probably could be tied to some other potential, we don't know it, right? It could be 0 or it could be something else. But if our P got some more potential than the source, then the problem will happen. So that's why to solve this issue, what we do, we always tap our body of NMOS to the lowest possible thing, which is ground probably, and the opposite thing for the PMOS, because in PMOS our body is N type, so N type should be highest possible potential, and in this circuit what is the highest possible potential, and that is VDD, so we always connect it to the VDD. And the best thing to avoid this forward bias situation is to just tie this body and source together. From the outer perspective we can see, yeah, our P and N would be in the same potential, so they will never in a position to get forward biased, right? So that's why we do this thing. But there are some other reason also, and that is the second question of us, and it is the body effect. Okay, so we will go there a little later, but let's explain it here. So here, if I want to my source and body together, so I need to interchange this thing, and we can do interchange thing because our MOSFET is a symmetric device, so we can interchange, is no issue. And the source and drain will get their name according to who is supplying the electron and who is draining the electron. So we connect source and body together always, and that will help us to avoid the body effect. But in every circuit this is not possible. If I can show you the example, but before that, if it is your inverter, right? So in inverter, actually it's very easy to connect our source and body. Here we are having source and body together. This array actually give you the body terminal. So source and body together, and here also source and body together, it is connected to ground, and this connected to VDD. In inverter it is all okay, but you can't do this every time, because for example, see this example here. This is perfect. PMOS source and body are tied together to VDD, but here you can see this is your source terminal of one of the NMOS, and it is tied not to body, not to ground, but to something else. But your source is connected to ground, and your body is connected to ground, and this body is connected to ground. So for this NMOS, for sure you will be having the body effect, and which we can't avoid. And this is because you just remember your body terminal is nothing but the substrate, and substrate is same for all the PMOS. So probably for manufacturing this all PMOS, we have a common substrate of P type, and then here we'll be having our NMOS, again another NMOS, and then we are probably having a N well, and here we are having P implants, so we have one PMOS, and again P implants, so we'll have another PMOS. But this whole substrate would be a common body for all the NMOS in my chip. So that's why all your body of NMOS will tied to ground, and this N-well could be the common body for all the PMOS, or at least for these two PMOS. So we will connect these to VDD. So that's why we don't maintain the thing that our body and source terminal are always tied together. We want to do that thing because to avoid the body effect. So now we'll explain what is body effect. So for interview, see, this tutorial series are not for your exam. For exam you need to show exact equations and everything to explain, but in interview you don't need to show them. So here I'll roughly tell you how to tackle this question in your interview if they ask you that what do you mean by body effect. So body effect appear anytime you disconnect your source terminal and your body terminal, and this happen always, many times. I have shown you one example here, right? So this happen always, and due to that what happened, and due to this body effect, actually the threshold voltage of your NMOS or PMOS can get modified. If you want to get more detail, then you need to explore those equations of your VT, of your threshold voltage. And if you explore your VT more, then you will find out there we have a term and which is directly proportional to your source body voltage. Increase your VT for NMOS, and the same thing can decrease your VT for PMOS. And in general we want VT should be constant throughout our circuits. So that's why we try to avoid body effect, but it is unavoidable in certain situations, for example here. Now there is another reason that why we always tie our body terminal to ground or to VDD, and that is to avoid the latch up, and latch up would be the third question for today, that what do you mean by latch up. So again, to understand your latch up, you actually need to know the concept of BJT, but we just want to avoid that concept right now. In roughly, if you want to see this thing, then this could be translated here. I have explained you how this thing came, and here you can just see this is one N terminal, right? Then this substrate here, it is of P type, and then again you have another N terminal here. So this could act as a your NPN BJT. And likewise, if you see here, then we have a P terminal here, right? And then this thing, if I just remove this blue line here, then here in the base section of your BJT you have a N region, and again you have a P region here, right? So it would be again another PNP, and they are connected in such a fashion that one of the collector of this BJT is connected to base of another BJT, and the collector of another BJT is connected to base of another BJT. So that means they have a loop here. So if one of the BJT get forward biased or it become on by any reason, and how they got on, and that is anytime you get a forward bias in your base emitter junction. So this is your base emitter junction, and base emitter junction, when it will get forward biased, if your N get a lower potential than the P region here, which is the full substrate, right? And we already had connected this P substrate or the body of NMOS to the lowest possible potential, and that is to the ground. So that means this will never be forward biased. So this for sure, if we don't have any negative potential in our circuit, there could be some way we get negative potential, and that time probably this can get forward biased. How? Because we have connected our body of NMOS or the P substrate to 0, but our this terminal N plus got connected to some negative potential. So that time we might forward bias this thing, but now we are not considering that we will have some negative potential, and we are saying no, negative potential probably doesn't exist in our this circuit. So that time if we connect our body to the ground for NMOS, then for sure this junction will always be reversed bias, and that means this BJT will be off for sure. Likewise, if we come to this BJT, right, then this junction, if I just remove this blue thing, then this junction, this your emitter and base junction, this junction should get a forward bias to make this thing on. So that's why we connect the N thing to the highest possible thing, and that is your VDD. I hope you got your answer why we don't do this thing and why this thing called latch up, and that is because one of the collector is connected to the base of another BJT, and likewise here. So if one of these become forward bias, then it will supply the current to the another BJT, and which will turn make it on, and it will again supply current to the next BJT. So anytime if this thing got forward biased, and you just remove the disturbance here, so that this junction got reverse biased again, but as it got the forward bias thing or the current, so it will make this BJT on, and this will supply the current again, and this current will in turn make this thing again forward bias, because your BJT could get on forward biased or with the current supplied to the base section. So likewise we will have a loop here, and which is a vicious cycle, and it will go on, and your MOSFET won't be working as you wanted. So you can roughly explain the latch up phenomena like this. So the three questions we discussed today are actually interlinked. So if they ask one, probably they will ask the following two questions also. You can tell them if any question arises from the body terminal, why it's connected, you can tell it is connected to avoid the latch up, and again we connect our body and source together to avoid the body effect. So that time probably your interviewer will ask what is body effect, so you can explain roughly, because they won't be asking you write down the exact formula here of VT. You can tell body effect is a phenomena which can increase or decrease my VT, and we don't want that thing, because most probably the performance of your circuits, because VT actually explain the sensitivity of your MOSFET or everything, with how much voltage it can become on or off. So if the VT is not fixed or it is keep on changing or it is dynamic because of your body effect, you can't predict the performance of your circuit correctly. So that's why we try to avoid our body effects, and that's why source and body are tied together. And also you can explain this latch-up phenomena roughly like this. Yeah, I know there could be some confusion about this BJT. I also have, because I never gone deep into BJT, but this type of intuitive answer could be okay for any interview, so don't worry. Don't invest your time to learn BJT right now. Now one interesting thing, and that is I have drawn inverter many times, right? This is our inverter, but anytime anybody tell you that, hey, design an inverter, what do you mean designing inverter mean? Is it means just to get your PMOS here and your NMOS here and tie them together? Is it this only? It should not be, right? There is some phenomena actually, and that is, if you just go to previous slide, then you can see it is dirty here, so let me make you see here. And that is, if this is your gauge section and this is your drain and the source section, then this is called your length, channel length of your MOSFET. And these things are in 3D, so we can extend them like this, right? So if I get out this width, so this will be called your W. And if you know the current equation of your MOSFET, then you will probably know that W by L have a great effect to your currents. And designing any circuit most probably imply fixing your W by L. So now tell me, if W by L is a ratio, right? It won't be having any unit. So if now I tell you this is my NMOS, NMOS have a W by L of 5, and I told you to design an inverter, then what would be the W by L of PMOS? Any idea? If you know the correct answer, then great, it's great. You just comment it down. If you don't know the answer, or if you know the answer but you don't know the reason, then the episode 4 will help you to get that answer, and probably that could be the more advanced level thing which will gonna explore from episode number 4 onward. So stay with me, and if you have seen till now, then please comment down and let me know you were here. It will increase my motivation. And don't forget to like this video. We'll see you in the next video very soon.